Today, the topic of discussion is on basic concept of strength of materials, that is module 1 part 3 PCME 403. Myself Dr. Suman Das, HOD, Department of Mechanical Engineering, Swami Vivekananda Institute of Science and Technology. So in this module, deformation in solids, physical and mechanical properties of structural materials, Hooke's law, stress and strain, tension, compression and shear stresses will be discussed. So bars with cross section varying in steps. A typical bar with cross section varying in steps and subjected to axial load as shown in this figure A. Let the length of the three portion L1, L2 and L3 and the respective cross-sectional area of the portion A1, A2 and A3 and E be the Young modulus of the material and P be the applied axial load. So that means in this diagram there is a bar of varying length and varying cross section. Okay, the applied load P is applied, that is at the end of the bar. Now this figure B shows the forces acting on the cross section of the three portion. It is obvious that to maintain equilibrium the load acting on each portion P is P only. So if we separate each portion, section 1, section 2 and section 3, if we see that, so the load P is applied in all the section. So stress, strain and extension of each section are listed below. So this will be the portion 1, portion 2 and portion 3. Portion 1 the stress sigma 1, portion 2 the sigma 2 and portion 3 the sigma 3. Corresponding the strain epsilon 1, epsilon 2 and epsilon 3, and finally the extension in the portion 1 del 1, del 2 and del 3 respectively in the portion 1, 2 and 3. So the total change in length of the bar, that will be del equals to del 1 plus del 2 plus del 3, that is nothing but PL1 by A1E plus PL2 by A2E plus PL3 by A3. So the sum of all the three extension. Now this is an example. So the bar shown in this figure is tested in universal testing machine. It is observed that at a load of 40 kilonewton, the total extension of the bar is 0.280 millimeter. Determine the Young modulus of the material. So we have to calculate the Young modulus of this material. Here the diameter and as well as the length of the bar. So everything is mentioned in this diagram. So what should be the solution? So solution is, first one is the extension of the portion 1. So from the formula we can easily calculate the value of extension. So we with the formula of PL by A, here PL1 by A1E, putting the value of P, the L1 the length of the portion, A1 the cross sectional area and E is the Young modulus or modulus of elasticity. In the same way for portion 2, PL2 by A2E, and in the same way the extension in the portion 3, that is PL3 by A3. So the total extension should be, that is the nothing but the sum of the three. So finally we are getting this value and this is equals to 0.280 as per the problem. So finally we are getting the value of E equals to, that is modulus of elasticity, equals to 200,990 Newton per millimeter square. The next one is the stepped bar shown in the figure is made up of two different materials. The material 1 has Young modulus 2 into 10 to the power 5 Newton per millimeter and millimeter square, while that material 2 is 1 into 10 to the power 5 Newton per millimeter square. Find the extension of the bar under a pool of 30 kilonewton if both the portions are 20 mm in thickness. That means thickness is mentioned here. So length of the bar, everything is mentioned here. So what you have to calculate? You have to calculate the extension of the bar. Now the steps of the solution. So cross-sectional area A1 and A2. So we can easily calculate the cross-sectional area. That is A1 800 millimeter square, A2 that is 600 millimeter square. So the extension of the portion 1 PL by AE, extension of the portion 2 PL2 by A2E. So with the help of the formula PL by AE formula, so we can easily calculate the value of portion 1 and portion 2. And the total extension of the bar, so that is nothing but the sum of the two. So finally that is 0.512 millimeter. Next problem, the bar of length 1000 mm and diameter 30 mm is centrally bored of 400 mm. The bore diameter is being 10 mm as shown in the figure under the load of 30 kilonewton. If the extension of the bar is 0.222 millimeter, what is the modulus of elasticity of the bar? That means here the E we have to calculate. So initially the length equals to 1000 minus 400. So that means the 400 is the bore length. So that is the L1 should be 600 and L2 equals to that is the 400 mm. So what is the solution? So cross section we have to calculate A1 and A2. So the cross section A1 equals to 225 pi, that is the pi by 4 d square formula. Similarly A2 equals to this with the help of the pi by 4 d square formula. We are getting the value of A1 and A2. So del equals to that is the extension the PL by AE formula. So with the help of that finally we are getting the total extension, the sum of the two, that is the del 1 plus del 2. So we are getting this. So that is final extension is that is given in the problem. So from this we are getting the value of E, that is modulus of elasticity, to 0.00726 Newton per millimeter square. Now we will discuss bar with continuously varying cross section. When the cross section varies continuously, an elemental length of the bar should be considered and general expression for elongation of the elemental length derived. Then the general expression should be integrated over entire length to get the total extension. This procedure is illustrated with this example. So that means with the help of example, we just explain. So what is the procedure? How to calculate? So here, that is the bar of uniform thickness. That is the thickness is T, and uniformly from the that is width is B1. B1 is the initial width, and B2 is the final width, and total length of the bar is L. So we have to calculate the expression of the change in length of the bar when subjected to an axial force P. So P is the axial force that is applied at the end of the bar. So this is the cross section, that means this is B and this is the thickness. Now the steps of the solution. So here consider an elemental length dx at a distance x from the larger end. So the rate of change of breadth, that is b1 minus b2 by L. So here the width of section x equals to b equals to b1 minus b2 by L into x. So that is nothing but so b minus kx. Here k equals to b1 minus b2 by L. That is the value of k. Now the cross-sectional area of the element, so that is nothing but A equals to thickness into that is width. So here the force acting at all the section is P only. So extension of the element we can easily calculate with the help of the formula PL by AE. So here P dx by AE. So put the value of that is the cross section, and we are getting this value. Now the total extension should be the integration of that. So we just integrate. So the lower limit is 0 and upper limit is L. So we integrating the extension of the element, this part, and finally we are getting this value. This is the value we are getting, that is the total extension of the bar. Now the example, that is a tapering rod has diameter d1 at the end, at one end, and it tapers uniformly to the diameter d2 at the other end in a length L as shown in the figure. If modulus of elasticity of the material is E is the Young modulus or modulus of elasticity, find its change in length when subjected to an axial force P. So this is the diagram, and this bar is the diameter is d1 and d2 as shown in the figure. The total length of the bar is L, and P is the load applied at the both the ends. So these are the steps of the solution. So change in diameter, that is L in L, that is d1 minus d2. Rate of change in diameter, that is K equals to d1 minus d2 by L. So now consider an elemental length of bar dx at a distance x from the larger end. The diameter of the bar at this section, that is d equals to nothing but d1 minus kx. So cross sectional area, that is A equals to pi by 4 d square formula. We just putting the value of d, bring value of d here. Now the extension of the element is nothing but p dx pi by 4 d1 minus k x square into E. So that is the extension of the element. Now extension of the entire element should be the integration of that, integration limit 0 to L. So we just putting this value, and finally we are getting this result, that is del equals to this. Now this is a note: for bar of uniform diameter, extension is PL by AE, and for the tapering rod, so it is the PL by pi by 4 d1 d2 into E. Thus the change is, instead of d2 for uniform bar, d1 d2 term appears if the bar tapers uniformly. Then another example. So steel flat thickness, steel flat of thickness 10 mm tapers uniformly from 60 mm at one end and 40 mm at other end in a length of 600 mm. If the bar is subjected to load of 80 kilonewton, find its extension. Value of E is given 2 into 10 to the power 5 megapascal. What is the percentage error if average area is used for calculating extension? What is the percentage of error? You have to calculate. So this is the given, that is T given, L given, B1, B2, P, that is force, that is value of M, that is 1 MPa equals to, we know that, so E equals to 2 into 10 to the power 5 Newton per millimeter square. Now the solution. Extension of the tapering bar for rectangular section, that is del equals to PL by AE formula. So here we put this directly, that is the extension, and we are getting the value of 0.4865 millimeter. If average cross section is considered instead of tapering cross section, extension is given by, so this is the value of del PL by AE, and this is the average, A is the average. So this is the average value, and del equals to this, and finally the percentage error should be the final minus initial divided by final. So ultimately we are getting the percentage error 1.384. Thank you.